Hello and welcome to chapter 12. Yes, awesome chapter here where we're going to analyze our analysis of variance. So we're going to describe a test of variance and then a test that simultaneously compares several population means to determine if they are equal. Yeah. So you know the drill. Here's our learning objectives. First off, we're going to apply the F distribution to test the hypothesis that two population variances are equal. Yes, a new distribution. So just like t values and z values, now we have the F. We're going to use our analysis of variance, or ANOVA, sounds like a superhero, to test a hypothesis that three or more population means are equal. We're going to use confidence intervals, yes, they're back, to test and interpret differences between pairs of population means. So, what is F distributions? What makes them? Well, they are a family of F distributions, each time the degrees of freedom. Basically, that's what F is. Is the degrees of freedom. And either the numerator or the denominator change, a new distribution is created. The F distribution is continuous. The F statistics cannot be negative. Sorry, it's always positive. The F distribution is positively skewed, though, too. And the F distribution is asymptomatic. So, to use the F distribution, the populations must follow a normal distribution, and the data must be at least interval scale. The value of F can be assumed an infinite number of values between 0 and positive infinity. Remember, can't be negative. The smallest value F can assume is 0. The long tail of the F distribution is to the right-hand side. As the values of F increase, the distribution approach the horizontal axis, but never touches it. Okay? So again, just like all of our other distributions, they're going to get very, very close to X, but they'll never touch that line. Okay? Whoop. All right. So when we compare two population variances, the value of F is computed using the following equation. Well, again, we have the sample variance squared, and both of them are going to be squared, but the larger of the two sample variances that we're going to use is placed in the numerator, which of course is the top. Okay, so it's sitting on top. The denominator is usually on the bottom. Yeah. So numerator on top, denominator on bottom. So always forcing the ratio to be at least 1. Okay. We calculate the sample standard deviation, S, and square the standard deviations to get the variances. That's why we have S squared for each population. Now, when we test whether two population variances are the same in the sample populations follow the normal distribution, we select a random sample of N1 from one population and a random sample of N2 from another population. Again, here's the example that we could use to test the two population variances are equal. Bum, bum, bum. Yes, we have lemurs, limos, L squared, because we're just all about squares today. So they offer a limousine service from Government Center in downtown Toledo, Ohio, to Metro Airport in Detroit. The president of the company is considering two routes. One is via US 25 and the other via I-75. He wants to study the time it takes to get to the airport using each route and compare the results. He collects the following sample data. Using the 0.10 significant level, is there a difference in the variance or variation in the driving times for the two routes? So again, we have to create our data set. As it shows how we get to our standard deviation. Gotta remember these formulas. So again, x bar equals the sum of all of our x's divided by the number in our population. Does it have to be the same? No, the sample population is going to be different, but it can still come out to our mean, or x bar, sample mean. Next, standard deviation is taking the sum, again, of all x, so the numbers, minus our mean, squared, divided by, since it's a sample size, n minus 1. Okay, so now we got our two standard deviations, which again, we'll have to square to get our variance. So once we conduct this test and figure out these, next, we're going to create our test. So we're going to state the null and an alternative hypothesis. So null is going to be our variance squared, or standard deviation squared, 1 equals our standard deviation of 2. All right? Both squared, and the other one is not equal. Notice again, because F distributions are about equal. Alright, so step 2, we're going to select the level of significance. Again, is 0.10. That is from the problem. The appropriate test statistics follow the F distribution. Again, state the decision rule, reject HO if the ratio of the sample variance is greater than 3.87. Okay, so how we figure this out? So to get the degrees of freedom in the numerator, we're going to take 7 minus 1, which equals 6. Okay. To figure out the degrees of freedom in the denominator, we're going to take 8 minus 1, which equals 7. So that's where we get the critical value of 3.87. Now, how did we get that? Okay, again, according to the rules, to the F formula, F distribution formula, to find F, you have to put the largest one in the numerator. 8.9947 is bigger than 4.3753. This is why we fall right here. Notice that it's also 0.05 because the level of significance that we know of is usually 2 tell. We're dividing it by 2 because what we're trying to do is find the little tell at the end. Whoop, went the wrong way. All right. So, we square the sample standard deviations to get the sample variance. We did decide to reject the null hypothesis. The test statistic 4.23, which is basically figuring out the formula right here, exceeds the critical value of 3.87. So they will want to consider the differences in variations in his scheduling. Basically, right here is where they calculate the actual formula. So, the decision is to reject a null because the test statistic of 4.23 is larger than the critical value of 3.87. They basically don't equal. Now, we conclude there is a difference in the variation in the time to travel the two routes. Mr. Lammers will want to consider this in his scheduling. Okay. Next, the ANOVA. So, one way ANOVA is used to compare two or more treatment means. ANOVA was first developed for use in agriculture. The term treatment was used to identify how different plots of land were treated with different fertilizers. Treatment is a source of variation. The assumptions underlying ANOVA are the populations are following that normal distribution, will have equal standard deviations, and the populations are independent. So again, they're independent of each other. They're not dependent. So they don't need each other to survive. So here's our example. We have Joyce Coleman manages a regional financial center. She wishes to compare the productivity as measured by the number of customers served among 3 employees. 4 days are randomly selected and the number of customers served by each employee is recorded. Is there a difference in the mean number of customers served? Okay, so we have Wolf, White, and Corosa. So they give us all the mu's, and we'll see if there's any change. So the chart in the middle illustrates how the populations would appear if there were a difference in treatment means. Note the distributions follow the normal distribution, and the variation in each population is the same, but the means are not the same. Suppose there is no difference in the treatment of means. This would indicate the population means are the same. This is shown in the chart on the right in the bottom. Again, the populations show the normal distributions and the variations in each of the populations is the same. So there's different ways of actually showing the data. So we're going to test it. Because why not? We're doing statistics. Let's test it. So first, find the overall mean of the 12 observations. So again, we're going to add them all up and divide by 12. Find out that's 58. Next, find the difference between each particular value and the overall mean. Square these differences and sum up. Okay. Result is the total variation here, 1,082. Okay. Again, this is a total variation is the sum of the square differences between each observation and their overall mean. Now, we're going to break this total variation into 2 components. Variation due to treatment variation and random variation. Treatment variation, the sum of the square differences between each treatment means and the grand of overall means. Random variation, the sum of the square differences between each observation and its treatment mean. So again, we got to know some stuff before we even get to the other. But it'll be fine. We're going to go through it. Okay. So recall that overall mean is 58, and the total variation is 1,082. Now break the total variation into 2 components. variation due to treatment variation, and random variation. How do we do this? Well, first off, the variation due to treatments is 992. We find this by squaring the difference between each treatment mean and the overall mean. And then multiply each square difference by the number of observations in each treatment. So since Wolf has 4, this is where we get 4 from. So they're going to take 56 minus 58, square it. Then they're going to add 70 minus 58 square, so forth and so on. Yeah. So each observation, and then they take the mean, which again, Wolf will have 56, Wright has 70, and Carosa has 48. That is their actual overall mean. Minus it from the over mean. So each treatment mean minus the overall mean squared times by how many observations are in each treatment. Okay, the random variation is 90, found by summing the square of differences between each value and the mean for each treatment. Okay, so this is the one where we take 55 minus 56 squared, okay, plus 54 minus 56 squared, all the way for theirs, and then at the bottom, once we get to Carosa's, since her mean is 48, 48 minus 48 squared is going to be 0, but that's how they're doing it. Okay? Seems a little bit more complicated than what it should be. But again, we have programs. So we'll look into that when we do the practice problems. Alright, we're going to calculate the test statistic F by, of course, taking the larger of the two, which most likely is always going to be variation due to treatments. And we're going to divide that by 2. That's because we have 3 treatments, so 3 samples. So 3 minus 1 is 2. Again, we're dealing with samples. Okay? Now, 90 divided by 9 right down here for the random. How do we get this one? How do we get the 9? Well, we have 12 observations and 3 treatments. So basically 12 minus 3. That's how they're going to be looking at it. Okay? Once we have this, we can equal out to 49.6. This ratio is quite different from I. We can conclude there is a difference in the mean number of customers served by the 3 employees. So, how do you find this? Let's go. So, finding the value of F and all of this madness. The formula for the sum of the squared total, SS total, sorry guys, still getting over COVID while I'm recording this, so talking for a while does flare up the coughing. Alright, what was I? Oh yeah, so the sum of the squared totals, SS total, is equal to the sum of x minus x bar g, okay, squared. Well, again, x bar g is the overall or grand mean, and x is in each sample observation. The formula for the sum of square error, SSE, is the sum of x minus x bar subscript c squared, which is the sample mean for treatment, for which treatment we're doing. So the treatment C. Now, formula for the sum of square treatment, SST, a lot of acronyms, is the SS total minus SSE. Again, we're trying to figure out a little error that could happen. And they have this nice little NOVA table here at the bottom, where of course treatments, again, sum of squares is SST, degrees of freedom is K minus 1. So the mean square is SST divided by K minus 1 equals MST. F is MST divided by MSE, which we gotta find the error. Again, SSE, N minus K. SSE is divided by N minus K equals MSE. And the totals are, add them up, we get the SS total. So it should equal right to the SS total. Degrees of freedom is N minus 1. And we're good to go. So of course, let's bring in an example. So a group of 4 airlines hired Brunner Marketing Research, Inc. to survey passengers regarding their level of satisfaction with a recent flight. 25 questions offered a range of possible answers: excellent, good, fair, poor. So the highest possible score was 100. Brunner randomly selected and surveyed passengers from the 4 airlines. Is there a difference in the mean satisfaction level among the 4 airlines? Again, since we're only looking for difference, when we want to do our test, we're looking at null, that the means for each 4 equal. And of course, our alternative is the opposite, that are not all equal. Now, some could be, but right now, we are testing it to make sure all 4 equal. Step 2, we're going to select the level of significance. We're going to use 0.01. Step 3, we're going to determine the test statistic. The test statistic follows the F distribution. Alright. Next, we're going to formulate the decision rule. We're going to reject the null if F is greater than 5.09. So how do we come up with this value of intersection? Again, using the table, we're going to take in K minus 1, which is 4, which is the excellent right there, minus 1, which equals 3. Okay, this is where, even though it's excellent, but we do have 4 different scores here. So 4 minus 1 will equal 3, where K equals the number of treatments. So 3 degrees of freedom in the numerator and down the column to row with N minus K. Okay, since there was 22, they're using 22 to minus 3. Yeah. So 22 minus 4 okay, yeah, that's the number of observations. So they made 22 observations, which yeah, they could have put that in there. Anyway, so Again, 22 observations minus 4 equals 18. Where again, we have n minus k. K is 4. That's the number of airlines we're using, number of treatments, minus the number of observations. Which again, they did not really give us. That is a poor example when they do that. Anyway, this is where we come up with 5.09. We look at the F table, and using the intersection of our numerator and denominator, comes up to 5.09. We can calculate the SS total, SSE, and SST with the given formulas, and then perform the calculations for F statistic. So again, using the formula from prior, right here, these ones right here, and the slides are going on their own. Okay. We can find that the treatment is 890.69. Error is 594.41. Total is 1,485.10. Degrees of freedom, we've already figured out. The numerator, which is the treatments, SST, is 3. Error is SSE at 18. Okay. Then we take our SST, again, divide by k minus 1, degrees of freedom. So basically, sum of squares divided by the degrees of freedom will come out to our MST, MSE, which we divide the 2. We get an F statistic of 8.99, which is greater than the critical value. So we reject the null hypothesis and conclude that populations are not equal. There's a difference in somewhere in the level of the 4 airlines. Pairs of the means. If a null hypothesis of equal treatment means is rejected, we can identify the pairs of means that differ with the following confidence intervals. Okay? Looks like we're going to have a little bit of fun here. So we're going to have the sum, well, not the sum, sorry, the mean of the first sample minus the mean of the second sample. Add and subtract, and our good friend t values back, using the degrees of freedom that are equal to n minus k. Okay, number of treatments. So the number of observations minus the number of treatments. Then we'll multiply it by the square root of MSE. Again, the mean sum error that we find in ANOVA, times 1 divided by the number of observations in the first sample, plus the 1 divided by the number of observations in the second sample. Again, yay, formulas! If the confidence interval includes 0, there is not a difference between the treatment means. Okay. Y'all ready for an example? It's like, no, but we're going to do it anyway because it's a chapter lecture. Oi. Pairs of means analysis example. Recall in the previous example of airline satisfaction. Because they can't get their satisfaction. We rejected the null hypothesis that the population means were equal. At least one of the airlines' means levels of satisfaction is different from the others. But we do not know which pairs. So we're going to figure it out. Use formula 12-5 to construct a confidence interval which the means scores of Northern and Branson using a 95% level of confidence. We find that endpoints are 10.457 and 26 0.05. Oh, that 0.43. Oh my God. Yeah. 0 is not an interval, so passengers on Northern rate service significantly different from those on Branson Airlines. So they used just one example. Hi, I'm so sorry, guys. But they would go through each of these pairs. So we have 4 pairs. So we'll have to go through 1, 2, 3, 4, 5, 6. But each pair, we're going to figure out the numbers. So we're going to take again a sample of 1, which happened to be Northern, minus Branson, which this is right here. Here's Northern Branson. So again, they go through all the information. So we find it's 87.25, which was the mean of Northern, minus the mean of Branson, which was 69, plus minus our T value, which we had to go look up in that 95% level of confidence. And square root the 33.023, which we had to figure out over here. No, it's not 33.02. Okay. Actually, it is 33.02. I'm looking at the wrong number. Sorry. Apologies. I know that's going to get annoying when you watch all the remaining lecture videos, because I'm not knowing when I'm going to get over this at the time of this recording. Alright, so 33.02, alright, figured out. There's our MSE. Oh. And then divide by 1, divide by 4, plus 1, divide by 6, because apparently there was 4 observations in the Northern, only 6 in Branson. Okay, then of course, we plus and minus the 18.25. This is where we get our endpoints. But we need one to hit 0. Notice, none of them hit 0. That means none of the pairs are actually going to be good. Actually, we should have Bronco and yeah. So again, yeah, notice all the results. So they actually did all the computations. Further, we can find that the Branson treatment is different from the WTA. Okay, note 0 is not an interval. And the Northern means, so find Northern. The Pocono treatment mean is different from the Northern mean. There it is. And the WTA treatment mean is different from the Northern mean. Okay. Since all of these intervals do not include 0. So the only 2 that actually include 0 is the Pocono Branson and WTA Pocono. Okay, so those may actually be equal. You may actually show that there's not a difference. Okay, so that's the big key. We want to make sure, again, 0 falls within. So does that mean that they're still the same? No, there still could be a difference, but it's not significant. So it's going to be very close. Alright, so I know the moment you're waiting for. Practice problems with your sick professor. Should have done that. Sorry. Okay. Alberton Media Research Inc. conducted a study of the iPod listening habits of men and women. One facet of the study involved the mean listening time. It was discovered that the mean listening time for a sample of 10 men was 35 minutes per day. The standard deviation was 10 minutes per day. The mean listening time for a sample of 12 women was also 35. But the standard deviation of the sample was 12 minutes. At the 0.10 significant level, can we conclude that there is a difference in variation in the listening times for men and women? Alright, state the null hypothesis and the alternative hypothesis. Well, of course, null is going to be the standard deviation squared of men 1 equal to the standard deviation squared of the women intervals. Alright. Okay, state the decision rule. Okay, so we have to figure out the decision rule. Which one will we use as a numerator and which one we're going to use as the denominator. So, we know the standard deviation, 12, is going to be the square. It's going to be larger, so that's going to be numerator, compared to 10 minutes per day. I am so sorry. Alright, so we need to go look up our F distribution. Okay, so since we're at 0.10 of significant, that's going to give us the 0.05. Remember, we got to divide that by 2. Okay. Next, to find F, we have to know that, of course, our numerator is going to be the 12 sample size, or 12. Minus 1 is 11. So we're going to find 11. And of course, it's not here. Went from 9, 10, and then skipped 11. Yay for the chart. Which is very odd. Okay, so we're going to have some fun on some of these charts. Alright, so the denominator is going to be 9. You know that. So it'll be falling right between 3.14 and 3.07. Which again, is funny that they did not include that. And looks like they don't include 11 on any chart. Let's try. Notice that we only got 2 F distributions, either 0.05 or 0.01. So, 2 different ones. But, that's always fun. So, let's see. We're supposed to be in between 3.14 and 3.07. If we have to look up an F chart, we probably could. I'm going to go ahead and tell you the answer is actually 3.10. It's about halfway between 3.14 and 3.07 because they did not give us the chart. So, again, we'll have to have our trendy calculator. 3.14 plus 3.7. Yeah, so about 3.10. We're going to have to do that. That's just about halfway between the two. And that will work for us. Okay. Next, we're going to compute the value of the test statistic, which is taking our numerator, 12. Again, that's our observations on top. The treatments squared divided by 10 squared. And remember, that always has to be the largest number on top. So 1.44 is our F. And then they want us to calculate p-value. Yay! And they literally say use a p-value calculator or statistical software. So we know how this works. Let's go find a p-value calculator for F distribution. All right. So, yay! Now, it's always good. Just look at Google. As you can see, Google will come with plenty of suggestions. But it does not hurt to Google this statistic. All right. So, F ratio value is going to be 1.44. DF dash numerator was 12. Actually, that was 11, sorry. Denominator is 9, because it looks at the degree of freedom. And technically our significant level is 0.10. Let's see what we get. Our p-value is 0.2969. Okay. If we look at that. Yeah, so every calculation. So, no matter what, the p-value is 0.29694. Okay. What if we use 12 and 10? Yeah. So, you have to use the ones that you actually calculated to get that F ratio. Okay. So, since F value, we would reject the null if F value is greater than 3.10. We already know that the F value is below at 1.44. Thus, we do not reject the null. Okay? So, get back to our actual problem so y'all can see. We do not reject the null. So, we calculate p-value. Again, I like how the book just states, use a p-value calculator. A lot of times with these, it's fine. Again, really quick, find a p-value calculator. Boom, done, over with. Probability is just too low. Anyway, so we don't reject the null, interpret the results. It is reasonable to conclude variations of the two populations could be the same. Okay, very similar, very close, so we can assume that we're probably going to have the same variations. Question 9. we're going to have a little bit more fun. Okay, so we're going to the ANOVA now. A real estate developer is considering investing in a shopping mall on the outskirts of Atlanta, Georgia. 3 parcels of land are being evaluated. Of particular importance is the income in the area surrounding the proposed mall. A random sample of the 4 families is selected near each proposed mall. Following all the sample results at the 0.05 significant level, can the developer conclude there is a difference in the mean income? So, can we conclude this? Well, what are the null and alternative hypotheses? Okay, so first off, simple as this, the null, again, since we're looking just for difference, is going to be that everything's equal. All the means are equal. And alternative is that they're not. Okay. Next, we need to find our critical value. So, again, our treatment is always going to be above our error. So SST over SSE. So again, let's get our calculator. And we know degrees of freedom for the treatment is taking the number of treatments minus 1. So we know our numerator is degrees of freedom is 2. Error. We have 12 observations. Okay. So 12 minus the 3 treatments or 3 samples comes out to 9 in degrees of freedom. So again, looking at our fancy table, and we're dealing with 0.5 significant level. We really have 0.1 and 0.5. That should be so for this one, we are not looking at dividing the 0.05, mostly because we're just dealing with more than 2, seems like. So, using the 0.5, it's always fun. Okay, we know the numerator was 2. Find 9. And this one is actually on here, so not the 11. Then we come out to 4.26. So we're going to reject the null if our f value, when we figure it out, is greater than 4.26. Yay! There it is. Just because I wanted to highlight. Alright, next, the fun part is to calculate all the formulas. So, biggest thing I want to probably do is put this in Excel. Alright. Like workbook. Alright. So we have 64, 68, 70, 60. And I'm going to actually put these all in. may have to insert more lines as we build it, but we're going to go ahead and use it this way so we can move across. An old orchard. We're just going to put old. I go waste time. 75, 80, 76, 78. Okay. So, we'll have to go to the formulas. Okay, so we're basically coming up with this chart right here. So we need to know the grand mean. Again, is the overall of all the numbers divided by, of course, 12. Alright. So, this is going to be SS total. We're going to get our Excel. First off, we need to find the grand mean. So we're going to go equal here. And we're going to put sum. So we're going to use the sum formula to help us out to add each 4. Add. Notice that I'm going to put them all in parentheses too. Remember that order of operations. PIMDOS. Always remember PIMDOS when you're putting in anything in Excel, because it's just like a big calculator. And remember to actually finish up the parentheses. But errors, they're usually correct. So, since this is going to be the grand mean, sounds like the grand poopah. But we have 12 observations. So we're going to take it and divide by 12. This shows us our grand mean is 71.25. Okay. So, we're going to create the SS total, which is x minus, again, x bar g. This is x bar g for r, the grand mean. And we're going to keep it so that we know what the formula is, x bar g, x bar g. So this is going to equal to our observation minus our grand mean. Okay. But we can scroll all the way down if we want to and get rid of the ones that have 0 or no value. There we go. Okay, next, remember, this is the sum of these. So to find SS total, we're going to equal to the sum of all these actually. We have to square them all, so we're going to square them. So x minus x bar g. It takes a bit. You always know it takes a little bit to piece these out, because you really need to piece them out to understand them. Now, is there probably formulas that are actually built into Excel for this? Yeah, probably are. But again, I want y'all to actually understand the formulas, how they break down each, and how to put them in. So, squared times itself. So again, calculate, boom, get rid of our zeros, even though they have no effect on this one, and find the total. Okay, so we have a large number here. It's usually always going to be a large number for the total. Okay. Next, I lost the formulas. Where are they? Alright. Well, I actually look up here on the Excel. Let's see this. I want to test the theory. So this equals sum and of course equals to this times itself. So we do get vastly different numbers. Okay, so be careful of that. That's what I wanted to test out on. So, different numbers to get to, sorry, that says total. Interesting. Alright, next, let's go ahead and figure out SSE. Which again was our n minus k, which again is the number of observations, minus how many we have, which is 3. So that's going to be 9. So SSE in itself that's actually degrees of freedom. I have to piece this out. So we're going to use the sum of x minus x bar C, which is the sample mean for treatment C. Yeah. Okay. I'm piecing this together and making sure the book was... Alright, So we're going to do it this way. I think using connect will actually help us out a little bit more. Alright, so variations do the treatment. So we got our grand. We're going to calculate both ways. So this was just doing our grand. Now, we're going to take and find the mean of each of these. So, mean, of course, is going to equal sum, this one, minus, not minus, divide by how many observations? Yes. So that is 65. Whoops. Okay. Do that. Okay, 71. Okay, again, a little piecing out. So we have 77.25. Now, sum of treatments. Basically, it's going to take difference between each of these means. So, this will equal and it's going to multiply by the number of observations. So, each of these are going to be squared times 4 because exponents is before multiplication. Let's see if there's an easier formula for square. I think it's just SQ. Square root. Power. Yeah, let's use power. So, that one minus R large. Okay, then we're going to square it. Okay, so again, see if we, okay, so I can't go 4 power, 4 multiply the power of that one, so 132.25, good. So we're going to use the same formula, since we have 4 observations, multiply it by power our mean minus our grand, then put comma for the formula, squared. Okay, then do it one more time, plus how many observations? We have 4. Multiply by power, again, old, their mean minus the grand mean squared, and that should be our treatment. A lot easier. Okay, and then we're going to do the same. Why the PowerPoint goes all cray-cray. Alright. I don't know why they try and go way overboard, and I was trying to do the actual table. It's a little off. The SS total. Okay? It's a little bit easier to do it the way that we just did. using this way. Alright, next, the random variation. Okay, this is going to take the difference between each value and the mean for each treatment. So again, basically I'm going to hide these two because I really don't think that was significant for our problem. Because we just want to find the f value, and this feels a little bit better way to do it. So we take each one, so x minus x bar. This one will equal to this minus their mean. And yes, should have known that was going to happen. So 65.5. There we go. There's those. And again, we're going to have to square them. So we can do it even better. We can go ahead and put the formula in. Or, no, actually, we're going to do it separate. So, x minus x bar again squared. Okay, so again, we've already figured out this is basically our SST. Now we're looking at SSE, which is basically our random. So this is going to equal boom. Okay, and we got to do it the same for all these. So this is going to equal that minus x bar, which is 71. Drag down. There we go. So equal to power, that one. Whoops. That one, comma 2. Okay. And last but not least, now I can see where they want to do the other way, because with more numbers as it gets, it can be a little bit more daunting. And again, there are formulas probably built in Excel to help make it quicker. But again, I'd rather you piece it out to understand what's going on instead of completely just relying on Excel. Okay. Next, we find the sum for all of them. So basically, all here, formulas, auto sum. So it ends up being about 87.75. Okay. So we actually figured them out. So SSE is 87.75. Next, we use the degrees of freedom. Remember, standard SAT was 2, because again, that was, the number of treatments or number of samples that we're doing, minus 1. And SSE was 9, because it's the total observations minus the number of treatments. Okay. So to find F, we're going to just go ahead and take these, 5 by 2, equal that divided by 9. Okay. Again, degrees of freedom. Then, finally, we take the 2. So, this is going, our F is going to equal 138.25 divided by 9.75, which comes out to 14.17, which is significantly greater. So we're going to reject the null. Okay. So again, we're going to find the p-value. Go to that friendly calculator that we found. Quick p-value. At 1.44, this is now 14.18. And our degrees of freedom have changed to be 2 and 9. Okay, at 0.05. Calculate. We're looking at a p-value of 0.0017, 1653. So the result is significant at p is, again, less than 0.05. Which means we're going to reject the null just based on the p-value alone, but we've already rejected it because of our rule. Critical value. Sounds a lot more complicated, but it really just takes the steps. I think the way that they try to do with your book, and again, that's the way I really do teach you, is they went kind of a little bit more heavy-handed right here, because as you saw that the SS total was not going to equal to the way that they have it, which is interesting in itself, but came out more close to this test to calculate the F. So, I would say go ahead and try to do it this way, the SST and the SSE. It's a little bit easier that way. Again, variation of treatments and random variation actually comes out to these two. Just different names. All right. One more practice problem. So, this one's a little bit similar. Yay! So, the following are 3 observations collected from treatment 1, or treatment I. 5 observations collected from treatment 2, and 4 observations collected from treatment 3. So, they're actually going with different levels now. Yay! So this makes life a whole lot more fun. No, it's actually going to be about the same. Okay, so again, we're dealing with the 0.05 significant level. So state the null hypothesis and alternative hypothesis. Okay, so again, our null is going to be them all equal. Our alternative is that they're not. I love those questions. Very simple. What is the decision rule? Well, we have to find F. Again, we're going to have to find the treatment, degrees of freedom, with those charts. So, back to our chart. We're going to go ahead and take that out. So, again, we're looking at 3 treatments. So 3 minus 1 is going to be 2. So that's our numerator. Treatment is always in the numerator when we're doing the ANOVA. Next, how many observations do we have? Well, according to this, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. They went back to 12. I don't know why they went back to 12, but they went back to 12. And everybody goes, oh, no. So, for our purposes, 12 is 9. So again, probably didn't even have to de-highlight it. It's going to be 4.26. So if our F test is greater than 4.26, then we know that we're going to reject the null. Okay. Now, they want us to compute SST, SSE, and SS total. Okay, cool thing is, we were smart enough, we already have our Excel still here. And again, SS total is just the sum of these two. So surprisingly, we already have quite a bit of numbers. And we're going to have to figure this one out one more time. Yay. But that's okay. Because guess what? It's already built in. Why is it already built in? Because we've already figured it. Okay, so we're going to see a lot of changes happen while we fill in stuff. So, I'm just going to call this T1, T2, and T3. And we all know T2 is the best of the series. Gotta love the battle of the two Terminators. Anyway, we're going to go ahead and fill this information out. And since we already have a lot of it programmed in Excel, let's see what it calculates out. And we are going to have to change some. Why? Because look at this formula. That has 4. We don't have 4. We have 3 now. This has negative 6.5. So we're going to have to change that. Oops. So now we're looking at 9.6667. So our best bet is to take each one of these and make them equal to that. This will give us an accurate result. Okay, delete that because that does not exist for us. We know we're going to have 5 here for T2. So insert a line. 3, 2, 1, 3, 2. And now it's 5. So again, if we're going to build out the table, might as well. Whoops. Go ahead and build out all the formulas. This way, you could probably use one Excel to compute everything. And this is gone. So make sure. Miss. Oh, sorry, guys. So sorry. Make sure your sum's in all of them. Notice again, that these are all changing. Okay. Sorry. We may have to go through here, and we may have to change because the power values have changed as well. So, again, it's the number of observations in each one. So this is now 3, and this is going to be 5. So you may have to change it just slightly on some, like when they increase the number. If it's smaller, because it's 0 right there, it's not going to affect. But Excel is going to actually tell you by putting those nice little triangles. So T3, last one, 3, 4, 5, 4. Change. This one pretty much is almost set up. Again, equal to this. All right. So, once we have figured it out, we have figured out our standard T. Let's see if there's anything in the formula that we have to change, which of course we type that in. We should just use that. Okay, so our SSE is 9.46 repeated. So according to the problem, we may want to just round to 2 decimal places. So we're going to go ahead and trim it down. Now I only trim it down here to make it look better in case we do need 2 decimal places, but it still has the full number since we're using the actual number. We didn't type it in this time. Okay, that way now anytime that I have to use the ANOVA, we already have everything able to calculate. We just have to adjust the numbers. So all this is already calculated in. So our total, I am so sorry, is 116.67. Again, if I want to round to 2 decimal places, I can. Our degrees of freedom, still 2 and 9. So those are the 2 numbers that you do have to put in on this formula each time. Now we could develop a formula, but it's just probably going to be easier just to put degrees of freedom. We come out to 53.6, 1.05. Then of course divide gives us our F, which again 50.96 is significantly higher than 4.26, which means null is going to be rejected. At least one means is different. Okay. F. If we rejected a null, so back to our problem. Can we conclude the treatment 1 and treatment 2 differ? Use a 95% level of confidence. Alright. So this means we're going to have to find t-value. Yay! So again, I'm going to use formulas. So Excel, since Excel has our info, except for t-value, we know the formula. If I scroll all the way back, whoops. Sorry about that. If we scroll all the way back, right here, here's our formula. So they're looking for treatment 1 and treatment 2. Okay, so taking this, so our formula, okay, is taking treatment 1, so again, this is means, the means of each one. So we already have it. So we're going to go equal our treatment 1 mean minus our treatment 2 mean. Then we're going to go, that's 7.46, so forth and so on. Long number. Okay, so that's 1/2. Now remember, the second half is our t value multiplied by the square root of MSE. Again, 1 divided by N1 plus 1 divided by N2. So each sample size. So now we got to go find our t value so that we can put it in our final formula that we're about to create. So t value. Okay, so since we're dealing with equals, we do know it's a two-tail, but it also has confident intervals, so we know it's 0.95. Put this on blue. Try and remove these so less confusing. Okay, so we're in column 3. Next, we have to figure out the degrees of freedom, which so this is a little tricky though. So where we deal with this is degrees of freedom. Now, t value still takes all the observations from all 3 treatments. Okay? So, it makes it a little bit more fun. Back to our t-chart. So, since we have 12 observations, even though we're looking at just 2, 1 and 2, we have 12 in total from all 3 treatments. So we're going to take 12 minus 3 because we have 3 treatments. This leaves us 9. Our t value ends up being 2.262. Okay. Get rid of these. So at 95% level, our t value is actually 2.262. So back to our Excel. Sorry. So our formula is taking our t value, okay, 2.262, and it's going to multiply, formulas, math, all the way to our square root. And the number itself is going to be our MSE, which is this number, since we already have the table, multiply by 1 divided by our number of observations in treatment 1, which is 3, plus 1 divided by the number of treatments in observation 2. Okay. Click OK. Okay. Comes out to about 1.69. Now to find our range, we would take 7.4 minus 1.69, and then do the same but add the 2. Okay, so again, as you can see, while I'm trying to do Excel, I'm trying to build out the formulas so I know exactly piece by piece and where I may need to change my observations. So anytime you have to hard put in a number, remember you have to change that every time. That's fine. But other ones, that if once you build it out, means it already calculates for you. So most of this will calculate for me and come out to the right answer. I just need to put in a few numbers. Alright, so my range is going to be 5.772 So, low end is 5.772, high end is 9.16. Since this range does not have 0 in between, basically as 1 intervals, there is a conclusion that they have 2 different means, which means that they're not going to be the same. Now, can I do this for all of the observations? Sure. I can eventually calculate them all out. That's if we need to. But we're not going to do that. We're going to just answer the question that we have. So, that concludes Chapter 12 lecture. Please let me know if you have any questions. We're going to move on to the next chapter.